so this is the other part of what I wanted to look at today, exponential graphs. We've already looked at parent functions and transformations, but I wanted to get a little bit more detailed on exponential graphs. So here's another reminder that anything to the 0 power is 1. So if I'm graphing, these are all called growth functions because they're 2 to the x or 3 to the x. So the number here is bigger than 1. These are exponential decay functions, 1/2 to the x, 1/3 to the x, because they're a fraction. And it's a fraction less than 1. So if I had the number 4/3, 4/3 is actually a growth function because 4/3 is 1 and 1/3. So let's see. The key points that I want to graph are always around the origin. So if I made a table of values at -2, -1, 0, 1, and 2, 2 to the negative second power from our table of values is 1/4. 2 to the negative first is 1/2. Anything to the 0 power is 1, and then 2, and then 4. So this graph is a curve that goes through a y-intercept at 0, 1, 1, 2, and 2, 4. So there is an asymptote. So the asymptote is actually here at y equals 0. That might be hard for you to see. So I'm just going to dot the asymptote in red. So y equals 0 is the horizontal asymptote, similar to when we studied rational functions. Let's see if I can get closer here. Whoops. So the next one, get a little closer. There you go. So this next function is 3 to the x. So we're going to make a similar table of values for x and y, -2, -1, 0, 1, and 2. So 3 to the negative second power is 1/9. 3 to the negative first power is 1/3. Anything to the 0 power is 1. 3 to the first, 3 squared. So it's a similar looking graph. It's just a little bit steeper. So 1, 3 and 2, 9, it makes the graph steeper, but it still goes through that same y-intercept, and it still has an asymptote at y equals 0. The graph gets really close to 0, but you can't get a fraction to actually equal 0 because it keeps getting halved each time. All right, so let's look at two decay functions. Basically, 1/2 to the x is going to be this graph flipped over the y-axis. And same thing with 3 to the x and 1/3. It's going to be flipped over the y-axis. Think about your transformation rules, right? This is 3 to the negative x power. This is 2 to the negative x power because remember the negative x flips it over the y-axis. Isn't 2 to the negative first power 1/2? So when I reverse this and I do a table of values, -2, -1, 0, 1, and 2, if I am taking 1/2 and raising it to the negative second power, doesn't that take the reciprocal and square it? So I would get 4. And then the reciprocal is just 2. Anything to the 0 power is 1. 1/2 to the first is 1/2. 1/2 squared is 1/4. So -2, 4, and then -1, 2, 0, 1, 1/2, 1/4. It's that same graph that we just did up here, but it's been flipped over the y-axis. And here's my still asymptote at y equals 0. And if I do the same thing with this last graph, -2, -1, 0, 1, and 2, I'm at 9, 3, 1, 1/3, 1/9. So I'm just taking this set of points and just flipping them. So -2, 9, 3, 1, 1/3, 1/9. Dotted line at y equals 0. So the steepness for these two is the same, and these are a little bit less steep. So we're going to analyze kind of what all these graphs have in common now on the back page. All right, so an exponential function, this is just the definition of an exponential function. You've got an x and the exponent. So what if I have 2 as opposed to 1/2 as my base? So the domain of both of these functions is always going to be the same, all real numbers. I can go left and right as far as I want. The range, though, is always going to be y is greater than 0. So my domain for both of these will be all real numbers, but my range will always be y is greater than 0 for the parent functions. The y-intercept on both graphs went through 0, 1, because anything to the 0 power is 1. A growth function is increasing, which means that from left to right, it's going up. A exponential decay function is decreasing. So from left to right, it's going down. We said that y equals 0 is the horizontal asymptote for both. Both of these graphs are continuous. So continuous means as I graph this function, I never have to pick up my pencil. Discrete is when you might have to pick up your pencil, like a rational function is two discrete regions, but it's still continuous within those regions. A scatter plot might be another type of discrete function. And then this says, do any of the facts change if we change this to a 4 to the x or 8 to the x, or if I make this 1/4 to the x? So no, just changes the steepness, right? A graph that's 100 to the x would be extremely steep, just like 1/2 to the x or 1/100th to the x, it would change the steepness. And then here's showing you a review of all your transformation rules. So what does the b value do? So if you're adding or subtracting b to the function, it's your vertical shift. What does the c value do? If it's in the exponent, it's moving the x left and right, so it's your horizontal shift. And what does the plus or minus do? That's kind of if it's going to be concave up or down, flipped over the x-axis. So flip over the x-axis. I didn't mention something in front of the x. I just used it like this would be a fraction. So I didn't worry about flips over the y-axis with a different variable. So what I'd like you to do is, we know that the parent function is on the front page. Here's 2 to the x. So I would like you to try these 4 graphs. What does that do, left or right? Look at your transformation rules from last unit. What does this do, up or down? What does this do, flipping the graph? What does this do, flipping the graph or shifting it? So describe the transformation and sketch those 4 graphs. This is the only page you need to submit for today's work on Google Classroom.